Now here in the last section in 10.4, we're going to look at finding areas and arc lengths for polar curves. So let's first think about the problem of finding the area of a polar region. And what is a polar region? To be more precise, we can think of it as a region that is bounded between two angles, say angle alpha on one end, angle beta on another end. So those are two angles, and some polar curve, say r equals f of theta, as the other boundary. And so the area of the region that's bounded by these three things is a polar region. So take, for instance, here this picture below where we've got a polar region bounded between the angles A and B. How do we find the area? Well, one way is to decompose that region into smaller sectors, where each of these sectors can be an approximating sector. So it's sort of like creating a partition where we do subintervals. In this case, our partition is angles with delta theta, and each of these approximating sectors looks like this. Okay, where r would be f of theta for one side, and then the theta here would be some delta theta. And if we know that the area of the sector of a circle is 1/2 r squared theta, in this case it'll be 1/2 f of theta squared times delta theta to get the area of one of these sectors. And then we'll sum up the area of the whole region using these approximating sectors by summing up all of these approximating sectors, and then taking the limit as the number of those sectors goes to infinity. It approaches this integral from a to b of 1/2 f of theta squared d theta. Okay, so this is a Riemann sum that turns into this integral, and so this will be how we find the area of a polar region. So a region bounded by a polar curve. Okay. Or here we can think of it as our polar region. Again, it's between two angles, A and B. And some polar curve r equals f of theta. Okay. So the area of that region between those two angles and the curve r equals f of theta is given by the integral from a to b of 1/2 f of theta squared d theta. Or here we can think of it as 1/2 r squared d theta. So let's practice this with an example here. So find the area enclosed by one loop of the four-leafed rows r equals cosine of 2 theta. Okay, we graphed this in the previous section, but now we can kind of see the region that we're looking for is bounded between these two angles here, negative pi over 4 to positive pi over 4. However, we can also observe that there's some symmetry that perhaps we can exploit. For instance, I noticed that the region that we're looking for is really twice the region from 0 to pi over 4. So going from theta equals 0 on one end to theta equals pi over 4 on the other end, we get the half of the region that we're looking for. Okay, so we can do 2 times the integral from 0 to pi over 4, 1/2 f of theta, in this case is cosine 2 theta, squared. And then squaring this, we get cosine squared 2 theta. Here the 2 and the 1/2 divide. Now I can use my power reducing formula, which is 1/2 1 plus cosine of 4 theta. Okay, so there, to remind you, we're using the cosine squared, so 1/2 1 plus cosine 2x. But here it's 2 theta, so we're doubling it and it becomes 4 theta. And now integrating this, we get theta plus sine of 4 theta over 4. And then we'll evaluate from 0 to pi over 4. And that will give me pi over 4 plus sine of 4 times pi over 4 is sine of pi all over 4. And then notice when I evaluate it at 0, we get 0, sine of 0, so it's just minus 0. And of course sine of pi is also 0, so we're just left with 1/2 times pi over 4, which is pi over 8. Okay, so that gives us now the whole leaf. So we did 2 times half of the leaf to get the whole leaf, right? So that gives us the whole leaf then. The area of the whole leaf is pi over 8. And if I want the area of the whole curve, all the way through all 4 leaves, the whole curve, we would just multiply that by 4. So our whole area enclosed by all 4 leaves would be pi over 2. Okay, so let's try another example. In this case, we want to look at the region that's between 2 curves. Well, this is a little different than what we just did. So let's think about how we can set this one up. So now the idea is similar to what we were doing, but we've got an inner and an outer curve. So say our outer curve is r equals f of theta. And let's say our inner curve is r equals g of theta. Okay, and going from, again, theta equals a to theta equals b. So what's the area of the region between those 2 curves? We can just do integral from a to b of the outer curve first. So the area bounded by the outer curve, which is 1/2 f of theta squared, minus, and then we'll subtract away the area that's bounded by the inner curve, 1/2 g of theta squared. So we're going to just subtract the 2 areas. And that's exactly what we'll do here. So we have on the outside we have this curve r equals 3 sine theta, which is a circle of radius or of diameter 3, and intersecting that at the points pi over 6 and 5 pi over 6. Which, by the way, how would we find those points? We should equal the 2 equations to each other. So if I set so the cardioid 1 plus sine theta equal to the circle 3 sine theta, and then 1 equals 2 sine theta, I get sine theta equals 1/2. So that gives me the angles where they intersect, which is at sine theta equals 1/2 at pi over 6 and 5 pi over 6. So that's how we get our angles of intersection here at pi over 6 and 5 pi over 6. So those will be the two angles that bound the region. And then our outer curve would be r equals 3 sine theta. And our inner curve would be r equals 1 plus sine theta. Okay. Again, we could also exploit the symmetry in the graph, noticing that here, just doing integral from pi over 6 to pi over 2 would give us half of the region. Or we could go all the way from pi over 6 to 5 pi over 6, and then we don't have to worry about doubling it. So let's just do it all in one swoop so we can see how that's set up. So here the area would be integral from pi over 6 to 5 pi over 6, 1 half. So the outer radius was 3 sine theta. And then we'll square it, minus the inner curve, which was 1 plus sine theta, squared. So that's going to give us the area. Let's work it out. We'll do a little bit of simplifying first. So when I square each of these out, we get 9 sine squared theta minus 1 plus 2 sine theta plus sine squared theta. Okay. One thing I'll do first is I'll combine 9 sine squared theta minus sine squared theta, so we get 8 sine squared theta. Next, I'll replace sine squared theta here with our power reducing formula. We know sine squared theta is equal to 1 half 1 minus cosine of 2 theta. So this becomes 4, right? Because 8 times 1 half is 4. And then 1 minus cosine 2 theta. And then I'll combine some constant terms here. We got 4 minus 1 is 3. Okay. We got 3 minus 4 cosine 2 theta minus 2 sine theta. So now we're ready to integrate. So I'll scooch it up here. So integrating, we get 3 theta minus 4 sine 2 theta over 2 minus, or I'll say plus 2 cosine theta. And then evaluating from what we were doing from pi over 6 to 5 pi over 6. Okay, now a little bit of evaluating that we have to do now, but let's keep going. So I got 3 times 5 pi over 6 becomes 5 pi over 2. Because the 3 divides with the 6. And then 4 sine times, or sine of 2 times 5 pi over 6 would be 5 pi over 3. So we got 4 sine of 5 pi over 3 over 2. And actually here, let me just simplify the 4 over 2 while I'm at it. So we get 2 sine of 5 pi over 3 plus 2 cosine of 5 pi over 6. So we have to evaluate each of those, but then we also got to subtract minus all this evaluated at pi over 6. So we have 3 pi over 6, which is pi over 2. And then 2 sine of 2 times pi over 6, which is pi over 3, plus 2 cosine of pi over 6. Okay. And then a little bit of simplifying here to get our final results. So let me evaluate sine of 5 pi over 3, which is, I think, radical 3 over 2. So that's just minus radical 3. Cosine of 5 pi over 6 will be negative radical 3 over 2. So minus radical 3 there. And here we'll have pi over 2. Sine of pi over 3 is also radical 3 over 2. So that's minus radical 3. Cosine of pi over 6 is also radical 3 over 2, but there will be plus radical 3. Okay. And let's see, what can we finally get here? So I noticed the 5 pi over 2 minus pi over 2 gives me 4 pi over 2, which is 2 pi. Minus radical 3 minus negative radical 3, so those are gone. And then I got minus radical 3 minus radical 3, so minus 2 radical 3. And then timesing it by half, we just get pi minus radical 3. So a little bit of evaluating there to finish it up, but we get the result. Our area of this region between the two curves is pi minus square root of 3.